Sorry about that. Sorry about the wait. Let's get started. So do people remember where we were? I think we went there. Type declarations. What is going on here? Oh, okay, wrong thing. Okay, cool. I think we just done last lecture. We had done, oh, sorry, I will just also set this view. Video, we want to turn video on. Okay, we'll get there. Is video on? It should be on. There we go. Okay, great. Okay, I think we've got everything set up now. Okay, great. Okay, so yeah, last time we had just finished shortcutting logic, I think, and maybe we talked about blocks. Did we talk about blocks? Yes. Or just before blocks? Okay, great. Yeah, okay, so we were just going through some syntactic constructs last time, Julia syntactic constructs, and we're talking about how every expression you can write has a value. So blocks of code are just ways of grouping statements together. So if you want one thing to happen after the other, you can put them together into a block. And the value of this expression is just the last thing, just the last statement in that block. So you can see we get 3 out. So yeah, they provide a way of sequencing statements as well. So if we have some things that have side effects, those things just happen in order, as you can see there. So normally you wouldn't see just the block syntax begin end that much. It does occur in places, but normally you would see it inside of other block-like constructs. So like this function here has a sequence of statements inside of it. So x equals 0 is first, and then this while loop is second, and then the return x is last. And those things run in order. So yeah, it's an imperative language where things which occur in the order of the source code occur in the execution order. So if we have this function f, yeah, we would, and when we write code, like we could indent this however we liked. This would have the exact same meaning as that, but it would just look really confusing if we did it that way. So we generally follow the block structure of the language when we use indentation. So yeah, if we run f, we're doing a bunch of things, just iterating through the values from 1 to 9. And actually we're returning the last thing we ended up with. So that's what that 10 there is about. So that's like one confusing thing that you've probably seen a few times actually, is that there's a couple of things going on here in terms of what's being printed. Like one thing is that these print lines have side effects. They print to the screen. And another thing that's happening is this function f is returning something, and that value is being displayed by the REPL. So 2 entirely separate ways of getting things to the screen here. They're very different, and sometimes they can be confusing. Okay, yeah, and there's like a note here about for and while loops produce nothing. So if we have, so yeah, every piece of syntax has a value. So 1 to 10, and just do something that has no side effects. This value z is nothing in that case. That's just the value you get when you don't have anything useful to return from a statement. Sometimes it's useful to write a block with this syntax. I'd say this is pretty occasional, but this is equivalent to writing begin 1, 2, 3, end, like we had further up here. But this can be useful, like if you have an if statement and you want some kind of temporary variable to do something with. So you can write something like that, for instance. Just as an occasional thing you might want to do. If you have like a temporary variable that you want to introduce, this is like a really convenient thing you can do. You can just like introduce that temporary variable in the like condition of an if. And actually I might make that a little bit bigger for you. And then you can use it in the next part, which is the actual condition, because this is the value that's returned, right, by this block. So then the if, then the if will use this part as the condition, and this part's just a little bit of a temporary helper variable, for instance. So it's probably the main place I would find this kind of syntax useful. As we were saying, all sorts of things which don't have a useful value. Oh, can't spell. Will produce nothing, and that includes blocks which are empty. Oh, we've got nothing here. That's the empty block. So, I mean, that seems kind of useless, but there is actually places where this is quite useful. So say you want to do something based on a condition like this, and then what's the value of half of x going to be if this doesn't even execute? Well, what the meaning of this is exactly the same as the meaning of this, where the else part of this condition is just empty, which is an empty block, and you get nothing. So that can actually be really useful sometimes. Like it, oh, we don't have x. Let's have x. So let's have a, if we have an odd x, then we can do something later on. Like we could have some other code which intersperses that. And then later on, we want to use this thing if the same condition was true. So we could go if is nothing, if not nothing, sorry, half of x, and then do something. Whoops, can't spell. So at the moment, x is okay. So yeah, if we happen to have these two things in a function, then this kind of can be actually useful. You might have some sort of code in the middle, and then later on you want to just do this thing if this value, if this is executed, this part of it. So that can be quite a little useful pattern. Yeah, okay, so, and there's just like print line, for instance, is something that returns nothing. And here's another function which would return nothing because there's no useful value. It's the point of this function is to have a side effect. There's a question, does anyone know what the equivalent thing in C is? Yeah. Right, that is sort of equivalent. So what's not equivalent about it? Like, yes, that's the closest thing you can have. Exactly, yes. You can't, so in C, you have void. So like this could be a function void hello, and you would not return anything. But then you can't assign that to anything. And you can't use it as in part of another expression. So that's like a kind of way that like languages with statements are different from languages where everything's an expression. You can't like use those expressions, you can't plug them into other expressions and always kind of compose them together. Oh, and that leads on to this next section here. Like, why are we going on about expressions so much? And so that's kind of the point is like when you have a language where code is actually data as well, which it is in Julia, sometimes you might want to manipulate the code, the syntax of the language as actual data within the language. And that would be how this macro show is implemented, for instance. So things with at in front of them are macros. So in order for this to even work, you can't like write a function called show, which does this thing. Oh, sorry, I'll put a semicolon there so we don't get too confused. So what this is trying to do is print line and then this piece of syntax, x plus 1, which is done, and then it's going to show the value of that syntax, not the expression. And that's not possible to do with a function because a function will only see the value that's passed in. So with a function show, you would only get like 11 passed into the function. You don't get this access to the syntax. So yeah, if anybody wants to go and look at what syntax is in Julia, you can produce quoted syntax with this Some people call it the frowny face operator, but it's really just a colon with some brackets after it. So if you quote the syntax here, this is just the syntax. It's not a value. And you can have a look at what that actually is. It's a little tree, and you can go dig around inside of that and mess with the expressions of Julia. So that obeys order of operation and stuff. So you get a whole tree there. Yeah, so but we don't really have time to go into all of that in detail, but if you're curious, you can go and have a look. And the way that macros like show are implemented is by manipulating this expression tree before the compiler comes and actually evaluates those things. I think that's kind of like what this bit's talking about. Yeah, and macro is just sort of like a way of making your own syntax sugar. So syntax sugar is just nicer syntax for doing something which you'd have to like write a long expression for instance. So it's like an abbreviated syntax for something that you might want to do. And that's what macros are for. They're for making abbreviated syntax, because you could always go ahead and like just write this thing, print line x+1 equals x+1. And then whenever you changed this expression on the right-hand side, you would have to change the string as well. So yeah, a macro is a way of manipulating the syntax so that you can have reusable syntax, I guess, custom syntax. Yeah, okay. So kind of key thing in Julia is, so like metaprogramming, you can do some metaprogramming with macros, and that's good for some things. But generally speaking, you would want to arrange your programs around multiple dispatch. So that's basically you have a bunch of types and you put them into some functions, and the question is which version of the function will it actually call? So if you have, it's a good example. We'll see a bunch of examples actually later on. So yeah, so yeah, like it's kind of a key part of making good Julia programs is figuring out what functions you have, what types you have, and then implementing the functions which apply to those given types. Okay, so we're going to talk about functions. There is a lot of ways of writing functions, and there's a lot of features around the syntax of functions. It's going to be a whirlwind tour. Okay, so there's lots of ways. Here's the standard way that you would have seen already. You just use the function keyboard, and that's the name of the function. Nothing special there. And yeah, this is asking, yeah, why is the return value optional? Well, it's just because the last thing in this block would be returned anyway. So, okay, so that's the long form. And that kind of makes sense if you have some kind of long, that one's not long. The one we had before, like this one's pretty long. You do want to have a whole bunch of stuff written inside of there. So you'd use the function keyword and you'd name that function something, whatever you want to call it. But sometimes you just want, sometimes the implementation of a function is really short, and you might like to arrange your code to be a bit more compact. So there's actually a short form. So we've got, for instance, F2. This is exactly the same as F1. It does everything the same, but this is just a short way of writing that exact same thing. There's also anonymous functions. You can write this thing that means x maps to x squared. And this will be given its own type. This #9 is the name of that thing. And in this case, we've bound it to a constant called F3. Yeah, so there's lots of different ways of doing this, and there's even a syntax for writing anonymous functions. So this is functions with compiler-generated names. I guess they kind of don't have names, but they have a compiler-generated name. If you just omit the name of the function here, then yeah, you'll create an anonymous function. But yeah, there is. I'm not sure if this comment's relevant. I'm not sure we're going to extend this one. Anyway, these are strange things. Normally, I would suggest you just use this one if it's a long function, and if you do have a really short implementation, you might want to use this one. Yeah, so what's the type of a function? Yes, so this is a strange thing. If you type of F1, it'll abbreviate it back as type of F1 because the actual name of it is complicated, or it's like kind of maternal. So yeah, that's kind of confusing, but basically the point here is that every function gets a unique type. And there's no data associated with those types. So it's just a singleton type. So if you just wrote struct F1 end, that would be the same layout as this thing F1. Okay. Later on, we'll encounter things that are function-like, or they are functions, I guess they can be called, which have data inside them. That's extremely useful. So, but these ones here, if you just define them at top level, they don't. Yes? Question? Yes, absolutely. Yeah, so how do you do that? You just do this. You put the arguments in a tuple, and you can do this kind of thing. Although I can't call that thing. So I can set that to something, and then I can call it. So you just do that kind of thing. So yeah, why would you use anonymous functions? Sometimes you'd like to pass functions to other functions. So that's the case when you actually want to use those. And you just want a really short, often those things are just like a very short implementation. You want to embed it in some other code. So yeah, you would, and in that case, you would like to just kind of write it inline in all the other code that you're writing. Not write a separate function definition. Okay, so and so in Julia, functions have methods. So in this case, we've got this F1 function, which we only have one method. So this is an implementation of the methods, an implementation of this function for some particular types. So this type, we didn't specify what it was, but that means it's an any. So any type could be passed into here. In a minute, we'll see the way of defining like various different methods depending on which types it's implemented for. This is a bit of a funny thing. So it's not just things defined with the function keyword, which can be called. You can call any object if it has methods for it, but most objects don't have methods associated with them. So they're like, there's no methods for nothing. But yeah, F1 has one method, and we will in a minute see a few different methods defined for a single function. Yeah, so I mean, you can define methods for things which are built in, even like this is a funny little example where, like, as I said, any type can have methods associated with it. And this is an example where you define the way of calling a bool, which makes zero sense. It's a funny example, but you could do it. Okay, let's do this one because it's less confusing than that. So true. This makes zero sense. Do not do this. But yeah, it makes sense in other cases. Yeah, no, I'm not going to do that example. Okay, so getting to something a bit more useful. In Julia, we have nested functions or closures. So the idea of this is that you might, well, functions being first class values, you can also capture things from their surrounding scope, variables from their surrounding scope. So this is an example of that. So this is a function which makes a function. So it's going to return this little anonymous function. Or it might be clearer if I wrote it this way. I mean, this is the other way of writing that thing. So yeah, if we now call adder with 2, that's making this thing here. Now, what you can see is that there's this x here and there's this x in here. No, those are actually the same x. So this function here is closed over this variable and captured it into the object which is returned. So we can go add2 equals adder2. And we have a little object which can add 2 to things. Okay. I think I've said, okay. And if you want to look at the internal representation of something, you can use the dump function. That's quite useful if you want to know what's really going on. So if we dump the add2 thing, then we can see that it's this weird compiler generated type. That was the type of this function here. And it happens to have the value 2 inside of it. So we could do the same thing with other values. Okay, oh, and here's the example, which is longer. I think we've gone over those things. Oh yeah, and there's methods. This again has just one method. Okay, yeah. And if you wanted to write all of this stuff yourself, rather than writing this little thing here, you could do a much more verbose thing. You could make your own struct called adder, and basically the compiler expands that thing we just saw, this function here. It expands that into something along the lines of this. So it makes a new type. In this case, it's got this weird name, but we could call it something if we wanted to. And it defines a way of calling that type. So that's what this is about. It pulls out the value that's been captured and uses it. And then we could define a function which uses this type. And that whole thing works in the exact same way. So it's kind of mysterious, but then when you see what it expands to, it's not actually kind of that mysterious. Okay, type assertions. How are we doing for time? I'm just going to really quickly go through this section. Yeah, because I think there's more important things later on. So yeah, you can use the : operator. It has several meanings. One of the most important is actually one of them is type assertions, but I think that's something you'd more care about if the compiler itself is having trouble figuring out what the type of something is, and it's having some issues generating efficient code. You might want to write a type assert. And I mean, if this was a variable x, then you might write x as an int, and that would help the compiler along. Normally, you don't need to do that. You'd arrange your code another way usually just to make that work. Let's skip through that. The more important thing about this : operator is argument types. So this is a way of defining methods. So before I said you have functions, and then those functions have methods. And the methods define implementations for the different types that you might want to pass into that function. So this one says that if you have an int, then you're going to use this implementation for f. And you could broaden that. You could say, well, if x is a number, any number, then you're going to use this implementation for f. Or this one here is the broadest possible version, where that is equivalent to any. So when you just write a function without any type annotations, that just means these things are any. It can take any type. Yeah. So let's get on to dispatch, because I think this will become a lot more interesting once we get to that. So here's an example where we have something more interesting going on. So we have this example f, which is a function. It takes an x, and if that's an integer, we'll call this version of f this method. So that will return inputs an integer. And alternatively, here's another implementation, another method. If x is a string, then it will return inputs a string. Okay, so we can return, we'll see that's an integer in that case. If we put a string in, we get something as string out. If we put something else, we get a method error. So there's just no method that applies to f. There's no method of example f which matches a floating point number. So in that case, we just get a method error. And again, we can go and look at methods. Oops. And we can see now there's two methods for f. Okay, cool. Oh yeah, and okay, so yeah, you can have abstract types. So we could have this one. We've got an example f2. Yeah, good question. Does the order that we declare them in matter? No, it doesn't matter. So we could do these in any order. What Julia does behind the scenes is every time it sees one of these declarations for a method, it goes and adds that method to a global table, which contains all of which kind of lives in the Julia runtime and contains all the implementations of all different methods of example F2. So you can add them in any order, and that global table, after you've added them all, will be the same. Yeah, no, so that's right. Okay, so that's a good point. I think there's a little section later on, but what Julia will do is it will try and find the one that's the most specific. So even though this one matches, so this could take an integer if this didn't exist. And that would be a very misleading message in that case. Yeah, but like int is a type of any. So int is a subtype of any, so that's fine. So it could actually go in here if this didn't exist. But in this case, we've implemented both of them. So I put a complex number in, for instance. It's not an integer. Okay, yes. Oh, that's jumping ahead, but great. Can you do multiple dispatch with keywords? Arguments, no. So positional arguments only are what count for multiple dispatch. We will get to multiple dispatch. If we don't, then I've really failed on time. But let's on being on time. let's not do that. Yeah. So yeah, we'll get to that. Okay, so that good question. You've foreshadowed this little bit of text here. Yeah, the most specific method is picked when you have like various methods that could apply to the same given concrete type. So in this example, we have multiple dispatch. So Julia is pretty unusual actually in having this feature. Most languages don't have multiple dispatch. Most languages just dispatch on the first thing, if that. So yeah, we can copy this thing over. So in this case, we have 4 methods, and we specified the types on both the arguments. So if they're 2 integers, if there's a string and an integer string, or a string and a string, we will dispatch to the appropriate implementation. We can see the methods. There's a whole bunch of them. Yeah, so most languages that have runtime dispatch don't have multiple dispatch. If they have any dispatch at all, they will have single dispatch on the first argument. So if you're using a language with classes, sort of object-oriented language, I guess, then you'll find that you can only dispatch on the first argument, which is the self in Python, for instance, or the this pointer in C++. So yeah, it's a lot less powerful in terms of the way that you select which methods to call. And that really has a big effect actually on the way that you structure Julia programs. Rather than when you have single dispatch, you kind of have the methods belonging to the first argument in some sense. With multiple dispatch, the functions have their own identity, which is separate from any of the structures in your program. That's like really important to the way you structure Julia programs, because you can decide on the set of verbs that you have, which are the ways to do things. Those are the functions. You decide on those things, and you decide on the types which go into those functions, and you kind of like get to choose those things independently. You don't have to tie all of your verbs to your nouns. So that's like, it has a big effect actually when you design large Julia programs. So yeah. And I guess I would say that like that's probably one of the biggest things to learn if you're used to other languages. It's like you have this extra freedom, then you've got to decide like what do you do with it? How do you structure programs? And it's kind of different. You could do all the same things you do with programs with languages with classes, but you end up structuring things other ways because it's like more expressive. Okay, so we've seen type parameters, or how to define different methods. There's also ways of slurping in a bunch of different inputs to functions without having to write down all the possibilities. So this one here, add all, takes a bunch of inputs, and these dots here mean that it's any number of inputs. So those things will be passed in as a tuple, that the inputs that you put in. So if we go add all, that will collect all of those arguments up into this inputs tuple and then run this code. Yeah, so you could do something more complicated, all sorts of complicated things with that, like this polynomial generator where you put the coefficients in, and then it would, this is a complicated example actually. It creates a closure which captures those coefficients inside of it, and then when you put an x in, it like sums these things up. So you can see it's putting x to the I times the coefficient. What is this? Oh yes, +1. Okay, that's funny, because we need the 0th term. Anyway, yeah. So this is kind of a complicated example, but it shows you a little kind of idea of what you can do with this, and it's very expressive. There's a lot of functionality packed into that small thing. Yes.
You say like want every argument, argument in that tuple could be a certain type, or like I want my coefficient.
Yes, you can. So let's do that. Let's say we wanted them to be, how are we going to use them in a minute? And anyway, it's there, you put it there. So this one, yeah, now applies. So all of the A's have to be int. That's kind of weird. You probably do something like this, or maybe number. Yeah, so you might do that kind of thing for sure. You can also have other arguments before this. That's fine too. Although it doesn't make sense in this example and doesn't make sense what I've written there. But yeah, you could apply some types to these, and then all of the following ones are this type. Yes?
If you wanted to do something like, if you want to have something which is like an arbitrary number of type 1 variables followed by an arbitrary number of type 2 variables, could you do that? Like to get those like operations, or is that not?
I think you can't do that. I should know the answer to that one, and I don't. Well, I think you can't. No. I don't think that works. Let's see. Yeah, see, you're only allowed to have one of those. You could probably get around that with some. Usually you can get around that kind of limitation by making like a generic one and then making some helper functions which kind of help you kind of match those arguments. But yeah, that's like a kind of tricky example. Sorry, no question. Yep, another question. Okay. Okay, so yeah, we've made this polynomial generator. Hopefully didn't break it by doing all those extra definitions. Let's go back to the original one. Oh. So that's that one. Yeah, so we could use the roots package to find the roots of these polynomials that we. I guess this is going to work. What's this polynomial? It's that one. We're to have that one. Yeah, so we could use find zeros to find the roots of this polynomial of ours. There you go. Yeah, so there's a lot going on here. Don't be worried if it's a little bit scary. There's a lot going on. There's a lot of syntax which comes together to produce that. Okay, you can have optional arguments as well. So in this example here, we have this last one, it has a default value. So it's just like writing two different methods, one which doesn't have this extra argument and one which does, and then calling the one which does have the argument with the value that you've provided. So that's just a shorthand. Keyword arguments are a bit more interesting, actually, I would say. So in this example here, oh, we don't have space to see it. We have this semicolon. That's the all-important semicolon. So what this semicolon says is like, these things are positional arguments. So everything before the semicolon is going to be filled up just based on the position you put arguments into this function. Then everything afterwards, you have to actually say the name of this thing to match it. So sigma here is going to be matched when you call the function with this sigma where you say the name of it in the call. Yeah, and to define the keyword arguments, you need that semicolon. That's what you need. Sorry?
By default, is there one that makes sense?
Yeah, right, exactly, yeah. So exactly. So these also have default values in this case. You can have keyword arguments without default values. It's allowed. But it's a little unusual. Sometimes you'll just do it for clarity because say you have a function which has a lot of configuration, like it has 20 different possible things you can have. Sometimes it just gets super confusing. If you ever see someone call that function in code, you have no idea what all of those different things you're passing in are because there's just so many of them. So sometimes you might use keyword arguments without default values, and that forces someone to write down what those things are so that the reader can actually like read the code and not go crazy. So yeah, this defines a probability density. In this case, they're also using the distributions package. Oh, that did not work. Tab completions failed me. Okay, another sort of feature of this is, so we saw before that we can slurp in all of the positional arguments with these dots. If you put a semicolon and you put some dots after a keyword argument parameter, you can also slurp in all of the keyword arguments. That tends to be useful when you want to defer the keyword arguments to some other function. So you've got your sort of wrapper function for someone else's keyword argument function, and you just want to pass all the keyword arguments you're provided to someone else's function. In this case, this very flexible function can be called with any number of arguments, positional arguments, 1, 2, 3, with any number of keywords. And yeah, you can see that you get these kind of objects that you can use. This basically can be thought of as a named tuple. This is mainly not a named tuple for historical reasons, unfortunately. It's pretty much a named tuple that we saw the other time. That kind of thing. So you can kind of pass that to other functions. Okay. Okay, so yeah, there's this little section here on destructuring. So when you can make a tuple and you can take it apart. So that's what this is about. So here we're constructing a tuple, and you can also take apart this tuple with kind of like the reverse syntax almost. You just put the brackets on the left-hand side of the assignment, and you get A and B. Whoops. A and B. So yeah, that can be pretty useful. Actually, one of the main places you find this is returning multiple values from functions. So if you want to return like 3 different values from a function, you can, let's do this. We'll just return 2 different things. Let's make it slightly more interesting. So we've got this function g, which just returns x and its square. And say we wanted to get those values into some variables so that we could use them. This is how you do that. Yeah, so that's what destructuring is about. Just you can take apart tuples and other things that can be iterated, basically. So you could take apart an array that way as well. Oh, you can also do this with named tuples. Don't do this though. Use the real and imag functions. RE and M are the field names of a complex. They're internal. Use real and imag. Yeah, so we'll just skip the rest of that. Okay, function composition and piping. You might see this syntax, so let's just like quickly cover it. This syntax, these pipes, this vertical bar and the greater than, lets you put some value into a function. So it's just another way of writing a call. The reason this is actually useful is when you're building up a data pipeline. Oh, okay, so sorry, this is a special font. This is just these characters, but sorry for the confusion here. This just means exactly the same thing as that. If I type those things and then do that, it puts them together in the font. So don't be confused by the triangle. Okay, so if you're writing, if you're sort of doing some calculation and you want to keep adding something to the end of the calculation, that's where these pipes are useful. So if you've applied the cos to something and then you want to, keep applying other functions to that. Now, this is kind of a trivial example, but it comes up particularly often in sort of like data science work, I guess, where you have these things that you're piping through might be a whole data frame, like a tabular data structure. And you might want to filter for like everything which has every row which has like some attributes, for instance. So then you'd have my data and then I'd pipe it into filter and then so like I don't know, the row has the rows the height of the person or whatever. This is going to get complicated. I'm not going to continue with that, but basically like you might want to keep piping it through and seeing what you get at each stage. And it's kind of convenient to just keep adding to the end of the expression. It's just like nice to type, basically.
In that example, the data frame.
Yeah, which I deleted already.
And you're piping it to the delta.
Yeah, it was about to become disgusting and complicated, so that's why I deleted it.
The data become the first argument, or does the delta call return like callable the data?
Yeah, so yeah, in the case that you're doing this, okay, it just data becomes the only argument of the thing on the right hand side. So I can show you an example of that in practice later if you want, like maybe in questions or something at the end. It's really useful, but it's probably too much to go into right now. But yeah, like that's basically where I would use piping is data science type work. You can also do composition. So this little circle that you would use in mathematics, it means the same thing. So that's the composition of cos and acos. So that is the identity over some small domain. If you want to type that, in fact, if you want to type any special symbol in Julia, you'd type the LaTeX name for that thing and type tab, and you'll get that symbol. Okay, dot syntax. Yeah, so composition symbols exact same as like normal mathematical composition. So in that case, you'd be applying the acos first and then the cos, whereas this is doing it the other direction. Good question. Okay, dot syntax. Okay, so this one's actually really useful. It's like a lot of these things, like you'll use them on occasion. This one, for at least for when you're working with arrays, is extremely useful. So Julia provides a way of mapping a function across an array. In fact, it's more than just mapping, but like for the most basic uses, it's mapping. So that means applying this function to every element in the array. So in this case, well, we have, so X range is that thing. The abbreviated form for it is that, a compact version of it, but this is what's in it. And if we want to apply cos to that, if we just do cos of that, that doesn't make sense. The cos of an array doesn't really have a consistent mathematical meaning. Some languages will just say, oh, it applies to every element of the array, but like that's not really mathematically correct. So Julia provides a way of saying, actually, we just want to apply it to the elements of this array. So that's what the dot is in that case. We just put a dot after any function. So yeah, we can do this with our own functions as well. So we have myfunc, which takes 2 arguments, and let's broadcast that across our X range and 10, for instance. Yeah, so you can also see that if these things are scalars, then they're just put in every slot, sort of next to the values of X. So that's kind of the extra functionality that broadcast provides on top of map, is that it kind of expands. If things are scalars or other shaped arrays, it tries to make them match up, so that it's just maximally convenient, I guess. So yeah, this is really useful. It works for your own functions. It works for the built-in functions. And this is also the same thing that you are doing when you use something like infix operators. So if you want to add 10 to every element, oh, that's actually confusing. We can't see all the values of this because there's something special going on, but yeah, so if you want to add 10 to every element, you can use infix notation if you want to. So that's great. Okay. Okay, we're almost up to break time. I might just go through one more section. Okay, so a bunch more about control flow. So what's this section? I don't know, like, so basically this is pointing out that yes, there's like a whole section in the Julia docs like devoted to control flow. There's the usual things that if you're used to languages, imperative languages, and you're writing loops, you can do break, continue, and those other kinds of things for control flow. That all works in Julia. You have goto and label if you really need to use goto, and you have unstructured control flow, then you can do that. But generally wouldn't need to do that. One thing that's really nice about Julia is the way that its for loops work. So this syntax here, so we've seen a bunch of for loops for all sorts of things. But the point of this example is to show that this iterable thing here could be any object that you create. So when you write for X in iterable, it actually means, so what the compiler, the second part of the compiler turns this into something that looks like this. So what it does is calls this function iterate, base.iterate. So that's a function that, well, it's got 338 methods. So that's a function that is defined for everything that can be iterated. So you can iterate strings, you can iterate arrays, you can iterate all sorts of things. And because those methods are defined, you can use all those different things in for loops. So if you want to make your own thing that can be iterated, then you just define this function called base.iterate, and it will work with the normal for loops which are built in. Yeah. Okay, and yeah, let's talk about exceptions briefly. One nice thing to, well, this provides a way of dealing with errors. So if you've used exceptions in any other language, then you will find this familiar. But yeah, so here's this example where you're trying to write a thing to invert a 2x2 matrix, a function. However, some matrices are not invertible, and also this implementation only works for 2x2s. So yeah, so this implementation, if the size of the input is not 2x2, then we're going to throw an error. There's a function called error for the cases where you can't be bothered writing like choosing a specific exception type. So if we put that in. So yeah, if it's not 2x2, it's going to throw an error, and this kind of escapes the context of this function. Let's see how it works. Oh. So we'll just put in something that's not 2x2. So yeah, oh, wait a minute. What's happened? It's a matrix, yeah, okay. We'll just put in some random size matrix. Yeah, so here's an error. So that's the error we've written here. And we sort of escape from the context of this function without having to kind of follow through with any of this other code. And it works from arbitrarily nested contexts. And so we could also put in something which is not invertible, like a 2x2 matrix of ones. And in that case, we're hitting this error path here, where the determinant of this little matrix is approximately 0, or exactly 0 in this case. So we're going here, and again, we just escape from the context of that function. And well, it probably works for random matrices. Presumably, Andy, when he wrote these notes, I got it right. Okay. What was this about? Oh, okay. Yeah. So this is just showing that in fact this does invert. If you time this inverse by itself, then you do get the identity back again. So we could do that. And is that actually true? Oh, it's true. Let's even show what that looks like. So if we multiply the inverse by A using our inverse that we wrote, then yeah, it's pretty much the identity. There's this little off diagonal bit. Does anyone know what that's about? Floating point error, yeah. Sorry, I heard it over here already. Yeah, it's floating point error, yeah. Exactly. So yeah, you never expect it to be exactly 0 there. Okay, so okay, one other example before we break. We'll just go to the end of. I'll go to the end of try and catch finally. So this example here, this is actually broken. I need to fix that. So say we had a bunch of functions that call each other. So this function f is going to use this my 2x2 inverse. These other functions are doing some other things, and they all eventually end up calling this inverse. So this one here could create an error. Well, what's going to happen if it does? What actually happens is you escape from that inner context without all of the intermediary functions having to do any error handling. So it's kind of the point. So if we call h with something that's not invertible, don't want that typo on the end there. Okay, so the point of this example here is to show that, well, yes, we got this error, and yes, we escaped all of these calls without, for instance, the implementation of G having to do any error handling itself. And also, the runtime has shown us something really useful here. So it's shown us which functions we were inside when this error happened. So it's showing this stack trace here. So that's really useful. If your program crashes, you will see one of these. You've probably seen some of these already. If you've written any amount of Julia code, you've probably seen a few of these. If we want to handle that error, so we don't, if we want to put some other function, let's copy this. So we're going to call age, but we're not going to crash if something bad happens. So this isn't well indented. Anyway, you hopefully get the idea. If we put try catch and we wrap something which might cause an exception in a try, we can handle that error, handle that exception inside the catch statement, and then the program will stop escaping through all the functions that you have called. So we can handle that exception. So in this, let's change that just to make it a little clearer. So you might find the @info macro useful. This is for logging. Just so like kind of prints things a little bit more prettily. Yeah, so we had an error. In fact, we could do something. Oh dear, keyboard shortcut issues. We could do something more useful. This isn't useful, but we could return something, for instance. Have some way of like recovering. Okay. Okay, that's enough for now. Oh, okay. Let's have, I don't know, a 10-minute break. I've gone a bit over time for the first lecture, but sorry about that. Yeah, break time.
So there was an error earlier
Mm-hmm.
saying that alert for it's not callable. You made a method for
Let me search for not callable. There's a few things are not callable. Yeah, what is that one about? Sorry, I can't see what's gone on here. Do you know what's gone on? Do you?
it's like in brackets multiplication. You get times thing. See where that
No, exactly. I can't see where in this example because I copied this out and it worked. So I'm not sure why this has happened. It's an interesting one. Calculate. So let's produce the exact example because I didn't do that one. No, so that's what I'd expect to happen, right? Like it should go in here and have an actual error, which makes sense. But in this case, it said it's a method error, which is completely inscrutable. I'm not sure what's happened here. This document is rendered, by the way, like by a piece of code that comes through and like reads all of these code blocks and then executes them and then puts the results in here. So sometimes there's an issue with the document and that's when you'll see these red things here. I don't know why this has happened. Like I didn't write these notes, but I am kind of going along and fixing bits and pieces as I find them. So yeah, maybe I can figure out why that has happened. Sometimes these errors even happen because this is such a long document and someone's to find something earlier in the document. And that conflicts. So like a lot of naughty things have been done in this document, to be quite honest. Like there's up here, there's someone like making there's that example where you make bool callable, which makes 0 sense, like probably not going to break anything, but makes 0 sense. And you saw yesterday, like me make, the last week, I mean, me make, like redefine what plus meant for integers and everything crashed. So like you can easily break things. So maybe that's kind of things happened, I don't know.
possible, like if you've got a function
Yeah.
that wants to like apply a function to every element of an array of integers, and you want to say that it takes a function that goes from integer to integer. It's a way to like specify the type system, like or a callable.
Yeah, great question. Okay, yeah. So do you have arrow types is like another way of stating that.
Yeah.
The answer is no. Julie does not have arrow types. The function types that it does have are all just subtypes of of function. So
So it's like,
but they don't have the types that go in and the types that go out as part of that type. Sorry, I didn't
like-
quite get it.
like, you're saying kind of just the type is the struct that kind of, or like under the hood, the struct that represents that function. And it's like, I guess the context, so when you do a closure, that has the context you've captured.
Right, yeah. So yeah, exactly. Yeah. So it's like you could imagine having functions where like the compiler magically figures out like what are the inputs and output types. Like the input types are fine, like we define those ourselves. The output type is like dependent on type inference. So it's not fine in Julia because Julia doesn't promise that type inference is going to produce like a concrete type or anything.
Yeah.
It could just give up and produce any because it got too complicated. So it's like not really feasible in Julia. Yeah.
If it makes sense. It kind of seems centered around just multiple dispatch. It kind of seems like there's other parts of the language where the type system isn't as strong as like.
I think it's more like the thing that like the choice that's been made to make it like feel more dynamic is
Yeah.
kind of the key thing. Like because you don't have to define types anyway, you can write a whole program without talking about types pretty much. And like usually type inference will make things fast for you anyway.
Yeah.
And sometimes it doesn't. But yeah, like type inference is not promised to compute like a typed result.
Yeah.
Yeah, so it can't infer the output type. Yeah. Yeah, so like as opposed to something like Haskell or something like a functional language, like where you have like there's strict guarantees about like what kinds of things you can express such that the output type can be computed, right?
Yeah.
But yeah, we don't make those guarantees.
Yeah, I guess the main reason I was thinking about it was like performance, but like I guess like having the function itself document itself going like, oh, this should take an into it, but it makes sense.
Yeah, like so you can you can define functions which have output types.
Yeah, I saw that. And,
Yeah, maybe that was that further up somewhere? I don't know.
oh, like I was Googling it.
Oh, okay, yeah. So you can do this thing. So people said not to do it. Oh, that's funny. That's funny. So I'm honestly not sure that I've ever written one of these. This also has an interesting and kind of specific meaning, which is possibly different from what you might expect, I guess. So you could do something like this. This is a stupid thing, of course. So we're going to go return. Oops. Okay, so now this might not look like it works, but it does actually work. And why I say that might not look like it works, like you're adding this float to X. So won't that be a float? Well, the answer is that what this means is that every returned value is converted to an int using the convert function.
Yeah.
So,
You guys like backed it out.
sorry.
You guys like backed it out.
Yeah, right, exactly. So like we could even put a float in there. And like it always returns an int. That's because what that means is this one. We just delete that. So like that's kind of a bit of a key part of Julia, is that usually there's some like syntax usually means something which is simpler. In like some other syntax you could just write by hand.
Yeah.
Like there's not that much magical going on. You could just write it in terms of functions if it's fancy syntax. Yeah, right, yeah.
I was wondering, well, like go to and label and stuff. But would that be something more functional, or is that?
No. So actually it's the other way around. The compilers, so the second part of the compiler, like
Yeah.
symbolic analysis / what we call lowering, I guess. So what it does is takes all the structure control flow, all the loops and things, and turns them into go-tos.
Okay.
So yeah, it's that way around.
So there's not much that relies on buttons.
No. Yeah, no, that's right. Yeah. So you could imagine the optimizer like, or the like language internals preserving this sort of block structure or maybe like hierarchical structure of the program. And like that's a valid thing to try and do. It's just that the way that people decided to do it was have the compiler work on an intermediate representation, which is just a big list of statements and go-tos between statements.
So it's mostly Julia's optimizer is just the LLVM one rather than having its own one. I guess like
Probably that's a pretty good assessment, actually. Yeah. Yeah. So it started out that way being true, but the Julia optimizer has actually evolved to the stage where it does quite a lot of stuff. So the type inference is not just type inference, it's optimization as well. So it actually does quite a lot. And then it passes it to LLVM. So it kind of like relies on LLVM for more the low level, like target specific stuff. But it does do quite a lot on the high level as well, in terms of like respecting or knowing things about Julia's language semantics, which are hard to express like to LLVM. Yeah. Sorry. It goes to symbolic label. So let's do this example, but then we got to get back into the next one. Don't know how I'm going to get through the rest of it. Okay, so like, oh, let's go. Oops, we do not have a label. So these are symbolic go-tos. So you just name the thing, that's the label, and that's the go-to. So that's how you use it. This is just a really bad way of doing an if statement, but you can do things that aren't structured control flow, and sometimes it's useful. So that just doesn't print a thing. So yeah, that's how you use it. Don't use it unless you really have to. Yeah. That just causes the compiler to reject your code. So it's like, no, it only causes problems for you. Yeah, there's a few other things you can't do, like you can't jump into a try and you can't jump. Like there's a few things that like illegal in terms of the like not respecting the structure control flow. You can't jump out of like a thing with a finally block. Yeah, there's a few different things, like, but mostly you can jump wherever you want to go. But yeah, not outside functions, of course, that makes no sense either. Yeah, for sure. Okay, let's get started on the next bit. Okay, where were we up to though? Thank you. We were up to errors and exceptions. Okay, so let's get started on the second lecture. Okay, so I just showed you try and catch. And there's also this finally thing. If you really want to, regardless of whether an exception was thrown or not, if you want to do a thing, then you can use the finally clause to make sure that you clean up anything. Okay, so yeah, so using those kinds of things, well, we saw that like you could escape from an inner context that with an exception, and it can like sort of bubble all the way out through the system. But sometimes like that might leave something, it might leave some resources uncleaned up. It might leave some things dirty, and sometimes you want to avoid that. So that's this example of the open function. Let's run this, but I don't want to call it open because there's already one. Let's call it open underscore, so it's ours, or my open or something. So this will, if you want to let the user do a thing, so that's this f, let's call this a function, in fact. So that's got to be a function. And we're going to open a file name and produce an IO object. We're going to let the user do something with that IO, and then we don't want to let an exception leave that file open, because if you do that kind of thing, you will run out of resources eventually. If you have lots of exceptions, your program will crash. So you'd like to close that file before you return, regardless of whether there was an exception or not. So that's how you write this thing. So the open function in Julia is pretty much this thing. Or there's a version of it. So we don't actually, I need to have a file to use this on. So what have we got? What files have we got? Oh, we've got like a make file, readme, okay. Okay, so we could run myopen. Okay, so there's some special syntax to allow you to use this. I guess that's the kind of point of this section. There's some special syntax to allow you to use this really easily and let you pass in a function f of your own to do something with the open file. That's what's called do syntax. So we can open the README, do IO, and we're going to read the first, well, in this case, 128 bytes for some reason of this file. So what this says, so this do syntax you might see around the place is, well, let's just do it. Okay, we can read that. That's fine. Let's convert it to a string so it's a little bit more readable. Okay, so this is the content of the start of the content of the README. So what this actually means is pass this function. So it's an anonymous function which does this read. That's what this syntax means. So like all the other fancy syntax in Julia, it's a shorthand for writing this thing in a more readable way. So make this little function, which that's its only argument, and then do this stuff inside of here. And this is injected into the first argument of myopen. So a lot of the built-in functions which deal with resources, like file handles like this, they will have a first argument, which is a function type, and then you can use the do syntax with it. So you can make your own ones of these. Variable scope. Oh yeah, let's skip through this section pretty quickly. So scoping is pretty complicated subject, but suffice to say, well, okay, let's just kind of quickly skip through the examples. So if you have a function, this x here is different from this x out here. Okay, fine. This is a local variable local to this function. So that example's about. You can make them explicitly local like that. That's usually not necessary to use the local keyword. Only if you have a top level block which is outside a function, you might sometimes want to do that. If you really want to assign to some global x, you could do this thing. You could say, well, x is global, so I'm going to modify the version in the global scope. Don't do that unless you really have to. All right, okay. So here's an example where local could be useful, I suppose. So we've got two functions here. Sorry, is this true? There is no. This is not the example I was after. This is the example I was after. Yeah, so you can use local to like define a new x, basically, which is local to some kind of block. and that's what's going on here. So this X here is actually a different X from the X outside. So whereas this one here will modify the X, which is outside this block, this one here will not. So that's the difference between those. Normally you just, like, my advice is generally just don't do that. Like, there's some specific cases where you might want to do that, but generally just don't do that because it's confusing to have two different things which are both called X, but are not the exact same X. If you do want to modify, like, for a for loop, if you do want to modify something in, or if you want this is like iteration variable to actually escape to the outer scope, you can use this outer thing, and that can sometimes be useful. Yeah, I'm just going to try and go through this section pretty quickly, because I'd really like to get to the example. Mutation. So we saw that, like, in terms of mutable variables, we saw that types can be mutable or immutable. And so this is like sort of an example of showing that the integers are immutable, but arrays are mutable. So you can change the values in a slot for an array. And yeah, when you pass a mutable object to a function, the data can be changed inside that mutable object. So just showing you can set things to something else. I'm going to skip this section because I think it's subtle and I don't know if it's that useful. Okay, but this is actually quite useful. So the abstract type tree. So we've seen some types that we defined ourselves, and we've seen some examples of functions which have sort of generic types like any, which they're allowed to take values of. So in Julia, all the types are arranged into a tree, and that's how we kind of have this notion of what is this, what is more specific when you try and select like some method to call. So let's have a look at this example. So the type of X is a float, and as I said, they're arranged into trees. So the supertype of that is an abstract float, and we can keep going down the tree. So abstract type is a subtype of real, which is a subtype of number, which is a subtype of any. And that allows you kind of this flexibility to define which functions apply to things by saying, oh, well, this function applies to, say, number, so it can apply to all these things. And also the other things which are numbers, like integers, which are not abstract floats, for instance. And you can use the is a function, which has an infix form. That's the way I'd write it. So 2.3 is a float 64. That just means that the type of this thing on the left is a subtype of that. Right, and we can ask for all these types which are arranged into trees. We can ask, are they abstract? Are they concrete? So the concrete ones are the ones which you can make a value of. And then the rest of them are abstract types or parameterized types. Oop. So float 64 is not abstract. These functions are built in to Julia. Oh, what's going on here? Okay, and oh, I've done it twice. Anyway, float 64 is not abstract, but it is concrete. And for something like complex, you'll find that it's neither abstract nor concrete, but it's more of a type constructor because you can put like int into complex to get a like a concrete complex type, like this one. So float 64 in that case. Okay, so here's the interesting example that I wanted to get to here. So this is a complicated looking function, but what this does is print the type tree. So if we look at all of the subtypes of number and we print them all out, we can see that we've got this big tree. So at the top, you've got number, And then you've got complex, you've got real, and there's all sorts of subtypes of real. Complex is parameterized, real is an abstract type. And then eventually you get to the leaves of these tree, which are all the concrete types. Yeah. And if you want to define your own abstract types, then yeah, you can use the abstract type syntax. And if you want to say where it lies in the tree, then you would use this kind of syntax. So real is a subtype of number. This one implicitly means that number is a subtype of any. You could write as a subtype of any on the end of here, if you wanted to. Okay, we've already seen complex, and complex is complex. It's a kind of union all. So what does that mean? So this is these parameterized types. So we've said way earlier, like in the previous lecture, that you can think of types as the set of all possible values. And so that's kind of, so it's a union of all possible values. So complex itself is this thing here. It's the union of all possible values of complex T, where T is a subtype of real. So, so it's this union all thing. Type of complex is a union all. So that's what you get if you have one of these parameterized types. You can also have abstract ones of those, by the way. And we've already seen union types previously, so I might just skip the union types section. So a lot of those things are like a bit in the weeds. You might not need, you don't necessarily need to know about all the ins and outs of how, like, Julia figures out like what is most specific, for instance, as a method, or like how all these types, or how exactly union all types work to use things. Like generally, don't worry about it too much. So here's the example. Here's the couple of examples that I really wanted to get to. So yeah, so we're going to make a little program which has some types and it has some functions. So it has some nouns and some verbs, if you like. So when you are doing some like physics problems, for instance, you often want to deal with units, and you would, in many languages, you would deal with that outside the program itself. Like the compiler might not give you any help for dealing with the units, but in Julia you can make types which represent, well, you can make types which values with units attached. So yeah, let's just make a little example where we have distance units. So we'll start with this little type here. So a meter being, it has a value of some type T, so that could be like a float. And the fact that it's called meter is going to be the thing which says, oh, it's a meter. It has, this thing is in meters. So, whoa. Oh, okay. Let's just reboot Julia here. I've run this example before. Okay, so we've got our struct meter. We can't do much with it at that point, but what we can do is override the base functions for dealing with numeric quantities in a way like this. So for instance, when you want to add two meters together, then you just add their values and then you wrap it back inside this meter type. So you retain the units on it. If you want to multiply a meter by some number, which is just a real number, this is not in meters, it's just a real number. So if you have something 3 meters long, then you just multiply that real number by the value of and then you wrap that back in a meter again. So you still have meters. If you want to divide 1 meter by another meter, so if you have 2 meters divided by half a meter, then you should get a number out, 4. You should not get a meter out of that. So we can define those algebraic rules in Julia, like by evaluating this block of code. So you can, see that on the right-hand side, some things are meters, some things are not meters. For instance, this one, And if we wanted to multiply 2 meters, we would need some more complicated units. Because we'd need to get meters squared out of that. We're not going to do that here. Okay, so to make it a little bit nicer, we could define this thing. Oh, whatever. What's going on here? Oh, there's a typo there. That's pretty funny. Okay, so I don't know if you've probably seen that Julia has juxtaposition to mean multiplication. And this is one of the few cases which makes that really compelling. I personally don't love it in many ways, but like this is one place where it's very compelling. So for dealing with unitful quantities, if you have a bunch of things which are just like the units, and also for imaginary numbers, actually, that's another place it's compelling. But yeah, so now we have 3.5 meters if we just type 3.5 m. And let's have it look a bit nicer. So we'll define this base.show overload. And now it looks like 3.5 meters as well. Okay. So yeah, like what's the point? Okay, so if we write our program and we do something incorrect, like try and add the number 1 to 3.5 meters, then it's an error. There's just no method matching. We should be adding 1 meter to 3.5 meters. That's fine, but adding number 1 doesn't make sense. And it's not slow. Julia's compiler will take apart all this stuff and yeah, it'll be fast at runtime, so that's good. Okay, so say we wanted to add some other units. This is like not super useful. Like we can do this thing with it, but and get like kind of an error so that we like improve the correctness of our program. But yeah, like let's add some more things. Okay, and like we could go crazy here. Like we're just doing length for now, but we could have a whole system of units and temperature and all sorts of stuff. And there's a package called unitful.jl, which actually does do that. So if we want to add all these different units, say we want to sort of add 2 of them together, all these different length units. Say we wanted to add 2 arbitrary length units together. Like how are we actually going to do that? One option would be, so like with multiple dispatch, you could imagine saying, well, you can define the plus function for like every possible combination of these types. But then if we have n different units, then we have to write n squared different functions. That's actually not even the worst part of it. Even worse, if someone else, like, so we implement this package with a few units in it, but then if someone else wants to come and add a new unit and then someone else over here wants to add another unit, there's like this kind of like quadratic growth of functions, and who's going to write all of those? Like which author of a package is actually is responsible for that? So that doesn't work. You can't write it that way. So one option to get around writing all of the different additions is to have one blessed unit. For instance, in this case, we're going to use meters, and we just convert every kind of length-like thing. We convert it to a meter. And then if we want to convert it to one of the other ones, we can convert the meter back to that other thing. So that's what we're actually going to do. You could have some clever rules. Like you have a subset of these n squared possible overloads of plus to say that, oh, if people started with imperial units, they should end with imperial units. You could do that if you wanted to, but we're not going to do that in this case. Okay, so, okay, we need to start this again, I think. Okay. So yeah, to show you how like kind of arrange code that does this, we're going to introduce this abstract type called abstract length. And now we're going to define all of these different length type units. So there's one for mile, inch, centimeter, kilometer. They all look the same inside, but they're different types. So they'll keep the units together with their value. So I can do all those. Okay, so then we can go ahead and do this thing that I was talking about before. We can define how things are converted to meters, and that's going to be our central kind of blessed type, where everything's converted through that. So this is how you do that. The constructor from meter, you can just add a bunch of different overloads to that. So if you put in a kilometer, then it should be 1,000 times bigger, and it's a meter, for instance. So we can add all those. Yeah, and there's this lovely imperial units one for what a mile is. And we'll just add this extra overload to make sure there's no ambiguities. So, okay, and in addition to that, we're going to want to go in the other direction. So converting a kilometer from a meter, and etc. So we're going to need those ones. Okay, so with that infrastructure in place, we know how to convert anything to a meter and anything back from a meter. So now if we want to convert between any two types, then we can just express it like this. So if X is an abstract length, and we want to convert to a kilometer, first we convert it to a meter, and then we convert it to a kilometer. So this is now like avoiding this n squared blow up, because we have this kind of central unit meter, which everything else is implemented in terms of. And we've also added these ones to say, okay, if it's a kilometer and you are converting it to itself, then it doesn't do anything, nothing changes. Okay. Yeah, and somebody else could come along. So I could have written this unit package with all these things inside of it, right? But someone else could come along and define a new one of a new type, which is a foot or something. And they wouldn't need to talk to me about doing that. They could just implement this themselves, and it would work with the rest of the infrastructure we've got in place here. In fact, we could even make it so that they don't need to write these. And this is the incantation to do that. It's quite the incantation, but basically it says if you're trying to convert to an abstract length from some other abstract length, then what you do is you convert it to a meter, and then you convert it to the original abstract length that you were trying to convert to. So this is like a way to generalize all of these rules here in a single rule. So yeah, don't worry if that looks hairy. It's actually confusing, but that's a way to write all of these rules with a single set of functions. Okay. So given that we've got those, wait a minute, what's going on here? We have seen all those already. I think this is, we had to restart this, so do those again. Okay. Right, okay, so we've defined what all of the base operators mean for meters. Now we could define what they mean for any abstract length, which is just convert it to meters and then use these rules. So that's what those ones are about. So yeah, if people put the meters in, they'll select these specific implementations, but if they put something else in, then they get these generic ones. Okay. Yeah, so you might want to kind of go through and like read over these again later to sort of see this. It's quite like it's quite a lot of infrastructure. But yeah, we will get to examples that work. So one more thing that we're going to need, or what we might want, is to preserve so like if you subtract to abstract, sorry, which one are we looking for here? yeah, so if we negate an abstract length, maybe we just want it to stay the same, like minus 10 centimeters is minus 10 centimeters, is not minus 0.1 meters. So if we want to do that, we can define this extra bit of infrastructure here, which is a new function called unit. So this will take any abstract length and return the unit for that abstract length. So there's implicitly, when you leave out the thing before the colons, this just means I'm not going to use the value. But you could just write x colon meter here equals meter. So basically the unit for something which is in meters is meters. So that's what that is giving you. And given that definition, yeah.
It's like unit dot t subset of abstract length is t.
T where t is an abstract. Yes. This one or? Yeah, right, exactly. So in fact, that would work. And we would need to write all these. I think that works. Wait a minute. No, okay. So what? No, that's not true actually. So that seems like it would work, but it doesn't quite work, because so what we're achieving here is like so if we have like 2 miles, this is an int64 version of 2 miles, right? So what we're doing here is actually stripping off that part of it, so we can get back to this type constructor. So yeah, there's probably a way to define a generic version of this actually, but you do have to deal with that problem. So yeah, it's just a bit more complicated. There's a way to define a generic version if you know what type. If you know that all of these things have exactly one type parameter, then like you could actually do the generic version. But let's pretend for the moment we can't. And sometimes maybe you couldn't, depending on like the structure of your types that people might want to overload. Yeah, good question. Okay, yeah. So using that definition of this new function, this new verb called unit, we can define some versions of these other operators. So like, for instance, negating a length that preserves the units. So if we have 10 centimeters and we negate 10 centimeters, then we still have centimeters afterwards is the point. So you can see what's happening, hopefully. When you negate an abstract length, then you negate the value, and then you apply the unit of that back to it to reconstruct something in the same units. This could be more interesting, for instance, in this case where you're multiplying. So why would that be interesting? 2.0 times centimeters 10. Now, the reason this is more interesting might be obvious now, because we started out with an int64 version of centimeters, and now we have a float64 version of centimeters. So yeah, that's why that does something a bit non-trivial. Oh no, okay, sorry, that is not right. I was worried if Yoni might be calling me for some reason, but no, it's all good. Okay. Sorry, I've temporarily forgotten what this example is about. Okay, let's run that example. So here's where adding abstract lengths. Yeah, thanks. Yeah, I'm just getting confused. So this one here would always convert to meters. But in this case, we're kind of going, oh, well, maybe it would be convenient if, yeah, we wanted to keep the units. So you could do this with dispatch rules, or you could do it with like just some logic. So it depends on what you're kind of going for. The reason you might do it with dispatch rules is if someone is needing to come along and override some things by adding more specific methods. If you do it with a function like this, then you will, like, someone can't override that logic. But if you did it with dispatch rules, then someone else can come along and add special versions. So there can be reasons. It depends on, like, this one's easy to express, but the other one might be more flexible. Okay, so we could do these things. Like we saw before, we can have some consts which represent the single, the unit of each of these. And we can add some niceties in terms of the way they're all displayed. Okay, so well, we finally get to more functional examples. So yeah, how many miles in a kilometer? Hopefully this actually works. There you go. And it's a number. It's not, it doesn't have units anymore. It's a multiple. Yeah, and you can answer things like this. This funny question with a whole bunch of different weird units in them. There's a ladder which is some centimeters high, and then there's somebody who's in feet and inches. And you can see something actually in this example, which is that nobody's defined feet. So there was still some like manual calculation going on here, but if we wanted to, we could define some feet, and this would be even nicer. So yeah, you can mix the units together, and in the end, you just get meters out because they're all different. I have no idea what's going on with the rendering of that because, well, yes, but yeah, something has been busted there. So we need to like re-upload this, I think. Anyway, yeah, so we're expressing in meters as we expect over here. Cool. Okay, so we've overloaded, like mostly here, we've overloaded existing functions in Julia. So like the arithmetic functions, but we could like add our own functions. In fact, we did add the unit function to help us to express like, yeah, like express the conversions in a convenient way. So yeah, how do we know to overload those base functions? Well, these functions are interfaces which are used like all over Julia. So if you go and look up what, like for instance, an array is meant to do, you should be able to get the value at an index. You should be able to get the length of the array, those kinds of things. So if you go and look up the Julia documentation, you'll find a section which says, well, the array interface, this abstract interface, it has, like if you make your own array, you should implement these 5 different functions or whatever. And so yeah, Julia has like informal interfaces. There's no like one place in the source code which says, this is the array interface. You actually need to go and look up the documentation. And if you want to make your own array, then you would need to implement a bunch of functions which are just sort of written down somewhere in the documentation. Yeah, so if we have our own abstract length interface, we can, so if we were to define that like we did in this example, then we would say to people, oh, well, if you want to make your own abstract length, then you need to implement these 3 different things or whatever it is. So conversion to and from a meter, you need to define a method for unit, which applies to your new length type. And you could, if you want to, define a unit value and an overload for show. And once you've done those 3 things, then your new unit will work with the rest of the unit infrastructure that we've built. And you find that like it's very lightweight. For instance, like an array, if you go and look up what is an array in Julia, like how do you define a read-only array, for instance, it's only about 3 or 4 different functions you need to implement, and then you can have your own array type, which does all of the fancy things. Like, for instance, you can do the broadcasting thing we saw earlier, where you map things across arrays. So yeah, Julia's interfaces are informal in the sense that, yeah, they're not like, you don't say like length implements like somewhere in the source code this particular interface, but they're very flexible. Okay, so yeah, and I mentioned before there's a package called unitful.jl. If you want to use that, then you can get all the different units, and you can yeah, you can do things like multiply meters and get meters squared. Okay, I don't really have that much time for this, and well, let's see how much we can get through of this one. So like now that we've made these units, we might want to use them for something more interesting. So in this example, we're going to have shapes. So a two-dimensional shape, and let's say that we've decided that the things that are important in our program about shapes are that we can calculate the perimeter and we can calculate the area. So no matter who defines the shape, they should define these two functions, and they can do operations on the shapes that relate to our program. So these are the verbs of our program, perimeter and area. So we'll define this. Now, these don't have implementations, you'll notice. There's no type, there's no arguments. So this is defining a method of methodless, oops. So 0 methods for this one. There are no shapes yet. Okay. So let's say we have a few different triangles. So these are all subtypes of shape 2D, and oh, sorry, we've got an abstract type triangle, which is a subtype of shape 2D, and we have these other ones. And let's have some quadrilaterals as well. So we've got a square with a side length and a rectangle with a width and a height. Okay. And oh, okay, we can have a circle as well with a radius. Cool. Okay, so given that we have these bunch of nouns, which are our different shapes, and we've got these two different verbs that we might want to implement with it for our shapes, yeah, we can just go ahead and actually just define the implementations for all of these different shapes. So for the perimeter of all of these shapes, we have a different formula. So we're going to add a whole pile of methods. So now we've got 5 different methods, one for each of our shapes. And we can do the same thing for area. So there's nothing surprising here. Just go through and like write them all down. Okay, and now we can actually finally compute something. Okay. Well, so we've got a rectangle and we can calculate its area and its perimeter. Okay, big deal. Okay, so, okay, that might seem like, okay, no big deal. We define on some simple verbs and some simple nouns, and we put them together. But where it gets really interesting is if we want to combine the previous example that we had, which had units, with our shapes. So let's have a square, which is has 4 centimeters on a side. So we can do that because we said before that our square could take any type t. And if we want to calculate the perimeter of that, we can do that as well. And we get 16, and it's centimeters. So that's pretty cool. Like these kind of 2 different, you can think of, imagine like 2 different people wrote these 2 different libraries, one to deal with shapes and one to deal with units. We'll wrap up in like a couple of minutes. Yeah, they compose together, and neither of these authors might need to know about the other author. And that's kind of through the power of having these interfaces and also having these generic types which are parameterized on some type t. So yeah, that's pretty cool. We can do some other examples. I'm not sure what's up with the millimeters here, honestly. Oh, so and this one's an interesting one. Okay, so yeah, that's an interesting one. So we'll just talk about that one very briefly. So we can get the area of a dimensional circle, but we can't get the area in our case yet of a circle with 10 centimeters, because that's because we don't have a square meter unit. So we didn't define something to deal with areas. So it's quite a lot of work to make something which does work with arbitrary kind of powers of units. And Unitful itself, Unitful.jl, has all of the infrastructure that you need to deal with that. It's like pretty non-trivial, actually. We could easily make something that deals with just like square meters, for instance. But if we want to have cube meters and meters to the 4th and all of the different options you might want to have, it's quite a lot of infrastructure. But yeah, you can definitely do it. And let's do that, in fact. So we'll just use, oh no. Okay, no, this isn't going to work. I don't have time for that. So the issue is that unitful itself also defines something called unit. So it just conflicted with what I was doing. But yeah, if we were to restart our Julia session and redefine all of those methods that we already had, then we could do this kind of thing and we would get square centimeters out. Yes, anyway. Okay, so that's the end really. We've covered a bunch of things about types and a bunch of things about functions and kind of seen how to mash them together a bit into a complete program. Yeah, and so that's kind of how you structure big Julia programs is you decide on your nouns and verbs. It's kind of as simple as that. And because functions are separate from types in Julia, that kind of works really well. Whereas it doesn't work so well in languages which think in terms of classes and methods belonging to classes. Yeah, anyway, we'll finish there.
Hi, I'd just like, can you hear me?
Yes, we can hear you.
Hey, Claire, I somehow can't hear you much, but I'd just like to thank
Oh,
you for
sorry.
these entertaining and very useful 3 hours. The class will part from Claire for about 6 lecture hours with Paul Verbeek, and then plenty of more very interesting things coming in the last third of the semester with Claire. So thanks a lot, Claire.
Yeah, you're welcome.
A message will come out for the quiz tomorrow. Good luck, everybody. Thanks. Bye-bye.
Yeah. Okay, yeah. So I can answer questions if people have more questions and you're still awake at this time, which you mostly seem to be somehow. Yeah, you're welcome. Yeah.
Parametric types.
Yes.
I noticed that you can use a symbol to parameterize a type.
You can do that, yes.
How and why?
Why would you do that?
What is that?
I love it. Yeah, what is that? Yeah, why would you do that?
I've been making
Mhm.
something and it was useful to have kind of like.
Thank you.
Yeah, see you in 3 or 4 weeks, whenever it is. Yeah.
It's like useful to have type aliases, and I needed lots of different types that were characterized by different things. So I just saw that you can use symbols to parameterize them, so I did that. But I don't understand like
Like
how
if-
was a symbol? Like how can I define a symbol and have that be its own type? How does Julia do that?
All right. Yeah. So okay. So the value. So yeah.
So it would be like
Yes. So I've
Yes.
got codes.
Yes.
So we can do this. Yeah. So it can have like struct whatever foo. Ooh, not type.
Yeah. Yeah.
And like this is allowed. So it's not just symbols. So any value, any bits type. So
Okay.
anything which is just made of bits essentially,
Yeah.
and is not like doesn't have pointers inside of it. Symbols are a special case, but yeah. So symbols work, but also other things work. Integers, floating point numbers work. All sorts of things work in there. So like, why would you do that?
Maps on the numbers you're using to parameterize.
Yeah, for sure. Yeah. Yeah. Okay. So let's do this.
Yeah.
Function f. It takes, I don't want to call it f, g. It takes an f, which is a foo of t. No, it's not t though. It's an n really.
Yeah. Yeah.
Like just for like making it easier to understand. But yeah, we can have n. You know, we can do this kind of thing, right? Now, so in fact, we didn't even need the f because in that case, because like if foo doesn't have any fields, so whatever, we'll just delete that.
Yeah.
So yeah, now g of a foo, which is 10 in it, should return 100, right? Now, what is the code typed of that? It's 100. So the optimizer, because this is a type and not a value, the optimizer knows perfectly well that we're putting in something with 10 in that slot. So it just like turns it into 100. It's perfectly happy to do that. Whereas if it was a value which we're putting in, then of course the optimizer couldn't do that. Now, like, why would that be useful? Well, like if you want to make an array which is like of a fixed length or something, that could be really useful, that kind of thing. There's like actually a lot of places where you would want to do that.
I was using the symbols for like making a tokenizer because it was annoying to have all the different things and. Like,
Ah.
so I was trying to make it. My initial thought was to use enums, but enums are weird.
They're definitely weird.
Like a macro,
Yes.
Like a single for each value.
Yeah, I don't love them. Yeah, they're like, yeah.
You can use symbols. And stuff.
Right, yeah, so like, you mean like, so what kind of token is it, like for a programming language
Yeah,
or?
like some sort of Lexer. And
Yes,
um,
okay,
yes, and so it'd be like, abstract token type left parenthesis.
yeah, you
Like
you
that.
can do that, yeah, so like foo of
type of-
symbol of like that kind of thing. I think that's
Yeah.
funny, but yeah.
I
And-
literally called it left parenthesis or right parenthesis, but that's probably a better way to do it.
Okay, so
Now that I know that I can use just regular stuff, I might use just the string representation instead.
right, yeah,
So you could have like, if you had floating type parameters, and you did like maths on, them, you could have like types that kind of should be equivalent but aren't, because they're floating to an error.
Yeah.
yeah, I guess so.
I was
Did you have a
thinking
question?
Like have a cursed abstract type that's like an abstract length that takes a parameter of like a set. And then that means you can do the unit operations by modifying the
Yes.
set.
Absolutely, you can. And that is basically how Unitful works. It has like a bunch of things which are not units, but they are like categories of units. So length is a category of units and mass is a category of units. So it has a slot, I could be wrong, but like roughly speaking, it is what it does. It has a slot for every category of unit. So if it's a squared length, then it'll have 2 in that slot. Yeah.
It's basically a little like 7x2 array where you've got like a coefficient and a power.
Yeah, that's the coefficient for, like, if you have,
So that you can represent inches.
oh, right, yeah. I don't actually know. Definitely you need the power. It might
You
deal with,
have one coefficient and then an array of like power, for like the 7 kind of SI.
yeah, so I don't know how it works exactly, but it definitely does. It has an array of like the powers for sure that needs that thing. And then you can get, yeah, that's exactly right though. Then you can get like arbitrary powers of units, and you don't need to have like a huge, like ever expanding amount of type infrastructure to deal with it, right?
The type system can check it. It's actually like in the type itself.
Yeah.
Yeah, that's true as well. And that's kind of how you, like, when I said it earlier, that's like, it's zero overhead in some sense, like the compiler removes all this stuff, like, because it knows like, oh, it has all that information in the type itself. Yeah, then it can kind of remove a lot of that during compilation.
It's like
Yeah,
10 types.
I don't know. Dependent type means something very specific in some languages.
Taking advantage of the kind of Java approach of just making everything nano-specific types, but without the overhead, but that kind of.
Yeah.
Without the like, yeah, pages of syntactic overhead
Yeah.
that Java has. Yeah, exactly. It's a very succinct language.
You don't have the university point
Yeah.
stuff programming.
So I think dependent types, isn't that a functional programming concept from like things like Haskell and stuff? I can't remember.
Yeah, Haskell doesn't have it, but it's usually only in like.
Or like Agda or one of those
Agda and
proof language. Yeah,
But then
yeah.
some languages now are having like, Rust calls them const generics.
Okay.
Kind of like you can use basic types in your type parameters. And in Rust, you can only do very basic operations on them, of course, because it
Okay.
actually has like file time.
Mm,
So it
mhm.
can't be doing like expression equivalence, checking arbitrary like complexity at runtime.
Okay.
Then Julia has the advantage that I guess if something doesn't work at compile time, it can just
Exactly. Just do it at runtime. Yeah, exactly. Like type inference can go, well, that one's too complicated. I'm giving up, which it is like it gives the language like a really dynamic feel, like everything works in the REPL and
Yeah.
it's fine. And so yeah, like you get that dynamism. like sometimes you might have something that doesn't type infer and then things are slow and you're like, oh no, what's going on? So then you need to use like one of the debugging packages to figure out what happened. So like there is downsides to it, but like the upsides are everything is interactive. So like that's kind of what you want.
For like data science and stuff. That makes
Yeah,
sense. Like,
exactly.
huge programs.
Yeah.
You kind of want to be able to pick up things at compile time as much as possible. Then, like, for data science, no data scientist wants to sit there annotating.
Yeah, yeah. No, that's right. Or maybe like only when you want to, like you want it to be fast in this particular case. So then you go to the effort of making it
Yeah.
fast, but otherwise you just don't care and you like everything's in any. Oh, and by the one thing like I didn't cover is like, even though you probably noticed that already, but like, even though you can have a method which is for any, that's only about dispatch. The compiler will still generate like specific versions of those functions.
Yeah.
Like, so like if I've got like, blah is like X. So I didn't really say what X was. So if I want to look at the native code for what happens if you stick in like a float, well, we need a bit more space here. So like that's tight. That's good native code. It's using like these intrinsics, like CPU intrinsics for doing multiplying floating point and adding floating point, and that's all that's inside this function. The rest of it's stack frame management, which will go away if it's inlined.
Like just two instructions.
Yeah, so you've got these two assembly instructions, like that's what you want, right? If you put in like an integer instead, well, okay, it's going to use the integer instructions because it's compiled down. So yeah, like it's not about code generation, it's about dispatch.
Yeah.
Yeah.
Yeah. Found it interesting that the Julia, the type tree, they've forced it to just be like kind of a strict tree where you only have like one parent, and then that kind of
Right, yeah.
for the dispatch, but then it also
Absolutely.
means you don't have that all your interfaces kind of have to be like informal. Whereas like in other languages, you can be like serializable and collection and this, but then dispatch gets quite tricky with that.
Yeah, that's right. So
It's like if you have two methods, one of them takes a serializable, one takes a collection, and then your thing is both of them. I don't know what Swift does in that case. I think it just does it for the first one. Also, it's like a similar dynamic dispatch, but
right.
I think it must just choose the first one, or
It may give you an error. So yeah. So Julia will give you an error. It'll just say this is ambiguous. In the case like multiple dispatch, you do end up with ambiguity sometimes. Like say you say that like the first parameter of something is an int and the second parameter is any, and then you define something the other way around where the second one's an int and the first one's an any, and now you call it with two ints. It's like, well, which one are you going to choose? Yeah. Yeah, so it's just an ambiguity error in that case. And the solution is, well, you need to tell it what to do. So do one, write one with two integers, for instance. Like that's one solution, or like another solution is to arrange dispatch differently. So what you do is you make just this function with both are any, and then you pass those things to helper functions. That can also be a really useful way to go about it. Yeah.
It's like Swift probably gets you to like cast this to an any serializable and this to a like cast this one to a serializable, so you lose that specific information.
Maybe, yeah. You can do that in Julia as well. You can say like invoke this one as if, like you can say invoke the abstract version of this thing. Yeah, it's like usually a sign that something has gone wrong somewhere in the design, like if you have to do that. But yeah, you can do it if you have to. And like very occasionally it's kind of sort of required where like someone's made an abstract version which you actually want to call from like a concrete version of something to implement part of it. And then you like get in trouble, so you can invoke the other one, but yuck. Yeah, if it's usually a sign that something's gone wrong.
With Julia, I think it always does the most specific one, whereas Swift, if the function takes an any, then that's erased, and if you call like a function inside it with that any, it'll always just choose that inner function that has an any, like it won't dynamic dispatch on the inside.
I lost you there, sorry.
Yeah, it's hard to like Because you've got a function f that takes an any and a function g with two methods. One takes an
Okay.
int and one takes an any.
Uh-huh.
Swift will always call g with an any. It won't, even if your input is an integer,
Oh,
because it compiles the code down to be like
oh,
generic on the input.
Uh-huh.
But there's only for the same input types, you only have like one.
yeah. So it's like the opposite of what I was just talking about, I guess. Like
Yeah.
here I'm saying, oh yeah, like code native is tight regardless of what type you put in, but
I
the
think
Swift is like,
inlines it, it will. Yeah, it might inline it, but
Y-
it will
yeah.
call the. If you specifically have it, if your code does a different thing for any, and like, if for any you've got a debug print or something,
yeah,
and for int, you just do it without debug print.
yeah.
This function, even if you give it, it'll do the debug print and then like use the generic.
Yeah, I may have gotten confused, but I think I might need to see it written.
F of x, which takes an any and then pulls g of
Let's
x.
like write it down
Yeah, Swift just assumes that it's.
in Julia syntax.
Swift doesn't look inside the
Yeah,
any.
so it's gonna call a different, which then calls a different function g of x.
So it's calling g of x. So is that situation or?
Yeah,
And then g of
Okay.
x has two methods.
Yes.
One is an int and one is an any.
let's just say they do completely different things.
Yeah.
Yeah,
You
okay.
want to just say, this is an int, this is not an int.
Yeah, this is an int and like g of any does. Well,
Like in
Um,
Swift, an int can still get to that
Yeah.
any
And
case.
so if you then call f of one,
yeah. So of course, yeah, in Julia, it's like, I don't know, does the sensible thing.
Well, if,
That is like very strange that that,
because in
yeah,
Swift, it's like compile time
right.
dispatch in that
Yeah,
sense, the
okay.
sense of multiple
Oh.
dispatch. It has to resolve it at compile time because it doesn't do any lookups. Like,
Right.
so. it
But
generates-
it sounds like it's generating for this function, which takes an any, it generates only a single one that can be called.
Yeah.
It generates.
Oh,
the
and that
same
makes sense. It's not a
functionality.
JIT.
It,
So it
Yeah.
has to do that.
it,
Yeah.
it generates one functionality, but if your code does give it an int, it might specialize it when it like compiles it.
Ah, I see. Yes.
Functionality, so it doesn't change the function.
Oh, maybe I see. Okay.
So like.
It's
compile-
confusing.
Yeah, like this one will always say, like, if that G did something, then generic with its input, like then.
Oh, not instead of well.
Yeah, it's hard to like think of an example.
So confused now.
I'm confused as well.
What's this
Like-
one meant to do? Is it called something else or like what does it do?
It's hard to come up with an example because it's also.
Oh, we've got something here.
This and that. You call f with 1000, but because there's only this one defined, it calls the any and returns should return high. So it should be.
The any version. That kind of makes sense to me.
Or compile, yeah. Because it's.
So
not
I
a
think
JIT, so-
maybe what you're saying is that like these actually correspond to the code that's compiled, whereas in Julia they don't. They just dispatch.
Yeah,
Yeah.
whereas like in Swift,
Yeah.
it will do the G1 and it can optimize it all at once, but it will always choose the same option. But now there's another feature where like.
See you next time.
Oh, yes, that's a different feature.
Yeah, anyway, that's interesting. Yeah, haven't written any Swift code, so I'm not.
It's very interesting just seeing the differences.
Yeah.
Swift has a lot of, thank you, it's like
Yeah, you're right.
a compile.
And by the way, if you're interested in tokenizers and stuff, look at juliasyntax.jl. juliasyntax.jl.
Okay.
So that's actually my project that I'm working on for work. The front end of the compiler.
Okay.
So yeah, I have a thing for tokens, which might interest you.
Oh, okay.
Anyway, it's not like reusable, so it might just be interesting in principle, like you can see how it's done.
Yeah.
But yeah,
Actually, I need to go, but.
Yeah.
Is there a way to like write? I don't know enough about LLVM, but. Like,
yeah,
Is there a way you can like write?
like LVMIR in
yeah,
Julia.
and then, like,
Yeah.
write it
Yeah, so you can use LLVM call, which is like a built-in intrinsic thing, which you can call LLVM code from Julia. So yeah, if you need to call some weird CPU intrinsic or something, you can totally do that.
Because I'm making
Yeah.
like a Turing machine compile. And I
Oh,
want it to be able to
awesome.
run-
It sounds
I want
great.
to like Julia library which compiles the Turing machine
Yeah,
and then runs it still within Julia, but it's running like a bytecode version of it.
yeah, awesome. Yeah, yeah, you should be able to do that. Yeah. Yeah, yeah, for sure. Yeah, yeah, you should be able to do it. That sounds like a fun project.
Yeah, it's,
Cool.
well, I guess, yeah.
You can
Swift
see ya.
has a lot of the same dynamic features, but they're like different just because it has to compile them. Like you can have structs that you can call
Mm-hmm.
and stuff, but you can't like pass them to a function that requires functions.
Yeah.
Like, whereas in Julia,
Hmm.
because you can't specify that you even want a function, just do whatever. You can't just
You can have structs you can call.
what decisions they have to make.
Yeah, yeah, for sure. Like it's interesting seeing what like language decisions you make. Yeah, to like, if we don't have a JIT available, then yeah, you have to make some
Yeah.
pretty different decisions.
So I think, yeah, like Swift, if you have